Hey everyone, welcome. Today, we're going to jump into the incredible world of biopolymers. You can think of them as nature's secret plastics. Let's get right into it. So, let me start by asking you a question, kind of like a riddle. What on earth could your car tires and your favorite scoop of ice cream possibly have in common? I know, it sounds a little crazy, but the answer is this amazing piece of chemistry that is literally all around us and even inside of us. You see, the secret is a massive family of materials that we call polymers. Now, over on the left, you've got your synthetic, petroleum-based plastics that we all know. But on the right, that's nature's version, biopolymers. The thing that connects them, the big secret, is their basic structure. They're all made of these long, repeating chains of molecules. And there it is. That's our answer. From the rubber that meets the road to the stuff that makes your dessert so creamy, it's all thanks to these incredibly long molecules called polymers. Okay, so before we dive into the whole bio side of things, we really need to get a handle on the polymer part. And here's the kicker. Humans did not invent polymers, not even close. Nature has been the absolute master of polymer chemistry for millions and millions of years. I mean, in the natural world, these huge polymer molecules, sometimes called macromolecules, they do just about everything. But what's truly mind-blowing is that they are part of a perfect, sustainable cycle. They don't end up in a landfill for 1,000 years. They just go back to the earth. All right, this brings us to something that's super important to clear up. The word bio gets tossed around all the time. And honestly, it can get pretty confusing. It can mean totally different things in different situations, so let's break it down. First, we have bio-based. This is all about the origin story. Where did it come from? A bio-based polymer is just one that's made from a renewable natural resource. Like corn or sugar, instead of being made from fossil fuels like oil. Simple as that. Next up, biocompatible. Now this one is all about how it plays with others, specifically with our own bodies. A biocompatible polymer is something that our body won't attack or reject. You see it all the time in things like medical implants that have to live inside us, without causing any trouble. And last but not least, biodegradable. This is all about the end of the line, the final chapter. A biodegradable polymer can be broken down by things like bacteria and other natural processes. It can actually return to nature instead of becoming permanent trash. Okay, pay attention, because this slide right here is absolutely critical to understanding all of this. These three terms are not interchangeable. People mix them up constantly. Just because something is bio-based, made from a plant, doesn't mean it's biodegradable, and a biocompatible implant in your body could very well be a synthetic plastic. Getting these distinctions right is everything. Phew! Okay, now that we've got the vocabulary down, let's take a tour of the incredible polymer factory that nature has been running for, well, basically forever. And just look at this diversity, it's amazing. From plants, we get things like natural rubber for our tires. From animals, you get casein from milk, which is used in glues. Even teeny tiny microorganisms make xanthan gum, which thickens our food. And pectin from fruit, that's what makes jam gel. They are literally everywhere. So to really see how these biopolymers work their magic, let's zoom in on two really cool examples. We're gonna go from our kitchen all the way out to the highway. So first up is xanthan gum. It's what's called a polysaccharide. That's just a fancy name for a sugar-based polymer. And get this, it's made by a tiny bacterium. How cool is that? We're literally using microbes to make things we use every single day. So where do you find this stuff? Well, go check the ingredients on your toothpaste or pudding or that ice cream in your freezer. It's in there. Its whole job is to be a thickener, to give those things that smooth, consistent texture we like. It's even used in heavy industry, like helping to get crude oil out of the ground. So how does it work? Well, it's basically a molecular shapeshifter. When it's a solid, its polymer chain is this nice, tidy, rigid spiral. But the moment you drop it in a liquid like water, that spiral unwinds into this big, tangled mess. And that molecular traffic jam is what makes the liquid thicker. So simple, but so brilliant. All right, so from our food and toothpaste, let's head out to the garage and talk about a biopolymer that actually keeps our modern world rolling along. We are talking about natural rubber. Its journey starts in a tree, the Hevea braziliensis tree, which makes a polymer called cis-polyisoprene. We harvest it as this milky liquid called latex. Then, that latex gets processed to turn it into the solid, bouncy rubber we all know and love, ready for thousands of products, but especially our tires. And here it is. This is the molecule that's responsible for everything. This specific shape is what gives natural rubber that incredible stretchiness. Those long chains can pull apart and then just snap right back into place. So, we've gone through the definitions, we've checked out some real-world examples. Let's zoom out one last time and think about the big picture, about why all of this really matters. This quote really just nails it. Nature's polymers aren't just useful, they're sustainable. They do all these amazing jobs without creating the kind of permanent garbage problem we have with so many of our synthetic plastics. This is the model we can and should learn from. So I'll just leave you with this thought. Nature's been a materials scientist for about 1 billion years, perfecting these polymers for every job you can imagine. As we try to find better, more sustainable ways to build our world, the real question is, what other secrets are just waiting for us in nature's designs? Thanks for joining me for this explainer.